Hey everyone, it's David with Streaming Relativity, home of the Astro DNA Observatory. So here we have two images of a very famous star formation region in the southern portion of the Serpens constellation. Of course, this is M16, also known as the Pillars of Creation. And one of the images was taken by the Hubble telescope, and the other was taken by the James Webb Space Telescope. Now, these are different instruments, and they have different scientific aspirations. But the images that NASA and the European Space Agency publish from these instruments, they're just so important. They not only educate scientists and amateurs alike, they're also probably the best advocacy tool for the field of astronomy. Now, my favorite, of course, is the 1995 Hubble image. And this image was so epic. It really affirmed the technical triumph of the Hubble program. I don't know if you all remember, but I was avid in the field at the time, and it got off to a pretty rough start. But this image really hammered home what a technical triumph that program has been, and it has provided so many insights relative to star formation and even planetary evolution. This is just an iconic photo, and it certainly captured the imagination of the entire public, including my own. And what makes this Hubble imagery so enduring, in my opinion, is that it's based on the visible light spectrum, just like our own rigs. Our own telescopes and our own cameras can capture the same spectrum of light as Hubble. So it kind of sets the bar for what a high-quality astrophotograph should look like. We'll never achieve that bar from the ground, but certainly it's something that we all strive for. And it absolutely provides inspiration to go out and find other examples of the same astronomical objects that Hubble has imaged. And that's exactly what I did this week, at the beginning of this week. M16 is an example of a stellar formation zone, and it's not the only example of these pillars of creation. In fact, it hangs pretty low. It's at negative 13 degrees or so in the constellation of Serpens, and that's difficult for me to reach. It's not as accessible as I'd like it to be to my observatory. So NGC 7822, the topic of this video, is another awesome example of this kind of stellar formation activity, and it's in the constellation Cepheus, which is 67, 68 degrees in declination, making it far more accessible to me as a Northern Hemisphere imager. And this is a terrific, very easy narrowband target, even with the full moon. In fact, I did all of the imaging during a full moon over 2 nights. So let's take a tour. We're going to take a tour of this DSO. We'll explore some of its features, its characteristics that make it so special, and then we'll cover how I captured it using my rig. And as always, I'll summarize at the end the Pixinsight workflow that I used to generate this beautiful image. And with that, if you are into astronomy and you're into astrophotography, you should subscribe to the channel. I put out content every week, and it's the best way for you to get notified when a new video is available. Okay, so I want to start this video with the session details, but before we dive into that, let's take in this image for a moment. And when we do tour it later in the video, we'll talk about the different features that we see, the different types of nebula in this region, the power source behind all of this illumination, and of course we'll get a closer look at some of these pillars of creation. But first, let me share how I set up to capture this image data, and make sure that you can do the same with your own rig and from your own backyard. Okay, I've gotten into this terrific habit of documenting my sessions using this format. I actually have a really a beautiful astrophotography journal that I've created with a lot of the images that I have been sharing with you guys. At any rate, this is NGC 7822, and we know that, and we know it's a star formation region. We know it's located in Cepheus. We'll take a closer look at that. But it also features a really cool open star cluster called Berkeley 59. Now, this particular DSO is located somewhere in between. It's actually, you know, if you're looking for it, it's in between Cepheus and Cassiopeia. And that's actually making it really easy to locate. And I took this image on March 24th. I started the image early that evening, and I ran it for 2 days straight. I had a really, really good seeing opportunity, a window here. And so I started around 8:42 in the evening. I'm in New York. I'm in about 41 degrees latitude, north latitude. And again, this is March. So from around 8:42, it just gets dark enough to begin imaging. And I ended on March 26th around 3 a.m. in the morning. And, you know, for those that are, you know, interested in the exact coordinates of this object, its right ascension is 0 hour, 2 minutes, 18 seconds, and its declination is 67 degrees north and 31 minutes, 16.4 seconds. Now, it was a full moon, and a lot of people won't image during a full moon, and I'm not sure that that's wise, especially if you're going to do narrowband targets. For me, I really enjoy producing images that I can share with my family, and they're not necessarily going to, you know, be the most discerning viewers of the image. They're just fascinated by the target. And when you're shooting narrowband, you can shoot during the full moon. So when you look at the my clear sky chart, you'll see that for both of these evenings, I had, you know, no clouds. And that's my biggest, clouds are the biggest thing that I can't stand, because you really cannot collect data through clouds. I used my Astro Tech 115 EDT refractor with a 0.8 reducer that nets out to around 644 millimeters of focal length. This is a strong hydrogen alpha signal that's where you're going to get a lot of this detail. I shot, this was an unusually long session for me. I shot 180 2-minute exposures. So we're talking about, well, you know, that's, what is that, 6 hours of hydrogen alpha. And I also shot about 3 hours of both sulfur and O3. So at any rate, this is a target where the more data, the better. Having said that, I think you can get with just one evening of clear skies and a good mount, wide field telescope, I think you can get a really nice image here with 3-4 hours worth of data. All right, let's go ahead and let's actually go through the image itself. Okay, I want to start by acknowledging that this is a beautiful astrophotograph, and of course I'm biased. I captured the data, I processed the data, but I truly think that it's a beautiful image. It's got great color balance. Clearly I used the show palette, so my sulfur is providing red, my hydrogen is providing green, and my oxygen is providing blue. And but the image has great depth, it has texture, good dynamic range in terms of different areas of brightness, and I think it's a strong composition for the story that I want to tell. And I think the most important thing about this is that it reinforces the importance of good data, and lots of it. Some of my nicest nebula images often feature 4 or 5 or 6 hours of narrowband channel data, and when you have a subject like NGC 7822, it's worth the extra imaging time. And if you can go 2 nights instead of 1, it will pay off for you. So, well, we know this is a relatively young star formation region. It's about 3,000 light years away from us, and to form stars, you need lots of space dust, and clearly there's a ton of it in this region. And this is a 22 light year a wide area, and it will easily fill a circular field of view at a radius of 2 to 3 degrees. So this is a big swath of sky. When we talk about deep sky objects, and in fact that there's so much dust in this stellar nursery that you get all three forms of nebula. You get dark nebula, you get emission nebula, you get reflection nebula, and that's always cool to see in one frame. Now, dark nebula, you can see very clearly in this image, and it's actually, some people get fooled by it. The dark nebula, do not think of that as a void in space, right? These dark areas are actually very, very thick clouds of dust where no light is able to pass through it. And any stars that you see typically on this type of area, in these types of, they're foreground stars. They're not behind this dust cloud. They're in front of the dust cloud. Now, there are brighter areas in this image where the gas appears illuminated. We generally call that diffuse nebula, and they're powered by the local stars in the region. And consider that all of this is being powered by a local star cluster that we call Berkeley 59. And it's located right here, this area of the image where you can see this cluster of stars. These are all bright, hot, large young stars. They're OB associations, where OB is the spectral types for the hottest stars in our universe. And so most of this diffuse nebula is being powered by that cluster. But one star is responsible for most of the illumination. So which one is it, do you think? Well, we'll zoom to it, and then you'll see. And there you go. It is this little star. It appears to be little to us because it's largely obscured by dust. But that star has a surface temperature of about 45,000 degrees Kelvin and a luminosity 100,000 times brighter than our sun. Again, it only seems small here because its brightness is obscured by all this molecular dust that it's illuminating. Now, we know a lot of this is emission nebula. We know that. We see that evidence in our hydrogen alpha stacks. And, really what's happening here is that these local stars, these stars are producing so much radiation that they're causing an ionization of the hydrogen in these dust clouds. And when that happens, you have an excitation and a relaxation of electron state, and that emits photons in a very particular bandwidth, which we can detect with our HA filters. Now, you can see that those areas, based on my color rendition, those are areas that are kind of a tan, reddish color. That's where most of that activity seems to be strongest. Now, you'll also notice that there's a blue region in here. There's blue wisps of clouds, let's call them. And this also is coming from that molecular dust and the energy from the stars, or the light from the stars, reaching it. Now, the difference here is that this is a reflection nebula. This is reflection nebula, meaning that the energy of these stars is not sufficient enough to actually cause any ionization of atoms. Rather, what we're saying that the visible light from these stars is bouncing off this molecular gas, and that's what causes it to appear blue, because these stars themselves are, in fact, young, hot, big blue stars. And so that's one of the most amazing things about this photo, in my opinion, is that we see the dark, almost black nebula. We see the glowing emission nebula in that red, tan, brown zone, and then we also see the blue reflection nebula. But that's not it. There's more to this picture. And just like the Pillars of Creation, M16, taken by Hubble and JWST, there are so many intricate dust columns and pillars and knots and pockets. That this is where the image gets its character. And the fate of these columns, there's only two possibilities for them. Either they will continue to coalesce and collapse upon themselves and give birth to what we call protostars, or basically the additional stars in this cluster, in this region. And they'll do that in groups. Or they will be blown away by the energy of their, of the stars that have been born before them. And in fact, these stars are going through their life cycle, and there's evidence that that a lot of this structure has been formed from previous supernova, right? So to some degree, we're looking at supernova remnants as well when we look at this star formation region. So yeah, this is just a great image. It's beautiful. It's a crowd pleaser. I shared it with my friends, my family. I got the wow reaction that you often get with some of these phenomenal objects. And listen, it's a terrific target for wide field instruments as well as longer focal lengths. And we'll see that in just a second when I review the high-level Pixinsight processing workflow. So with that, I hope you did enjoy the presentation of NGC 7822 and the Berkeley 59 star cluster. Okay, so obviously I've imaged NGC 7822 before with other rigs. Here we see some images, an image that I captured with my Celestron C8 Schmidt-Cassegrain telescope, and clearly the longer focal length allows us to get a more detailed view of some of the molecular cloud structures that are so famous in this region. Now, I share this simply, really more as a reference to a prior video I did on how to do color studies for images like NGC show images, narrowband show palette images, and I use NGC 7822 as the example. So I'm going to leave a link to that video in the description below. And I encourage you to go check that out because it'll be far more detailed than the high-level overview that I'll provide you now for the Pix Insight workflow that I use for the Astro Tech AT115 EDT image that I shared in this video. Okay, down to the quick overview of the Pixinsight processing workflow that I used for this image. As you know, I do all my stacking in Serial. I bring my stacks into a Pixinsight workspace, and I then align those images and do a dynamic crop to create what I feel to be a pleasing representation of the object. For this image, I did an automatic background extraction and a gradient correction. Remember, I was dealing with a full moon, so I felt that these two processes would neutralize the background for me, and they did an excellent job. Now, I chose to combine these in the linear state, so the non-stretched state, and when doing that with narrowband images or RGB images for that matter, you should run a linear fit against the channels. I did so using the sulfur channel as my reference. It was the least strong signal, so everything was fit against the sulfur channel. And then I was able to take the sulfur, the hydrogen, and the oxygen and use the channel combination tool to composite an RGB image. Now, the stars are going to look terrible when you do this for narrowband. And one way that you can address that is to use SPCC or a photometric calibration tool to try and get those colors properly represented. Now, remember, in order to use SPCC or any of these photometric calibration tools, you need to first plate solve for the image. So you can use the image solver for that purpose. Okay, at that point, I stretch the composition. I take it from the linear form to the nonlinear state, and I usually do that with histogram, the histogram tool, or that in combination with the curves tool. Now that I have a stretched image, I'll run a noise and a blur reduction, and I use RC Astro tools for this purpose. Small premium for them, but they're worth every penny. And once I at that point, I really have a representation of the image that is like my baseline. And generally speaking, I'll separate the stars at this point, especially if it's a nebulosity. I'll separate out the stars and then I'll work specifically on the backgrounds and see if I can't tweak them from a color and a levels perspective. And for me, the go-to tool of choice lately happens to be this narrowband normalization tool. And I think it's Bill Blanchard. And again, I'll leave a link to this in the description below. But I ran through that with, of course, applying a little bit of boost to the S2 signal because I was getting a bit of a washed out red signal. So I boost the S2 just a touch, to bring out a little more red and brown in those emission nebular areas. And once I was satisfied with that, I just recombined the stars. I use pixel math for that purpose. It's very well documented, the formula for this, but essentially I rescreened the stars on top of that background. And then I export this to a JPEG or a TIFF file, depends on what mood I'm in. And I bring that into GIMP, and I can do very, very fine tuning of the image. Actually, mostly so I can print it. If you aren't printing your images, I do encourage you to do so. Seeing your images in print is a totally different experience than viewing them on your monitor. But at any rate, I hope that this quick overview of the processing workflow is helpful, and that's exactly how I went about creating this wonderful image of NGC 7822. All right, with that, we're going to call it a wrap on the video. And I have to tell you, this image of NGC 7822 with the Berkeley 59 cluster makes a wonderful entry to my astrophotography journal. And I really enjoyed making this video. I really enjoyed capturing this image, the star formation region in Cepheus. I hope you enjoyed it as well. And if you did, and you like astronomy and all things astrophotography, please go ahead and subscribe. It doesn't hurt a bit. And it gets you notified every time I put out new content on the channel, which seems to be every week. And for those who are subscribed, then keep supplying me with those comments and those likes. Thank you so much. I really appreciate it. That's the type of stuff that keeps me going, keeps me sharing my passion for this hobby. And with that, I will see everyone on the next video.